speak.
Yes, I didn't see you completely. Good.
Okay. It gives me great pleasure to introduce again our friend Alexandru Buium from the University of New Mexico. Professor Buium was educated in Romania and was a researcher at the National Institute for Scientific Technical Research and at the Institute of Mathematics of the Romanian Academy. Came to the U.S., well, first I remember vividly, 1991 spring, and then again in 1993, and he has worked at Columbia University, the Institute for Advanced Study in Princeton, Max Planck Institute für Mathematik, where he was a Humboldt Fellow, has many, uncountably many papers, 3 research monographs.
It's already a contradiction.
And I would like to recommend to everyone, either here or abroad, Yuri Manin's 2013 survey of Ali's new theory of differentiation of integers called Numbers as Functions. And now Professor Buium will speak to us on the topic of arithmetic differential equations on GLN. Thank you for coming.
Thanks for inviting me to speak in the seminar. So yeah, the title is Arithmetic Differential Equations. Differential equations on GLN. And it's about mostly work that I did jointly with one of my students, Taylor Dupuy, and more recently with Malik Barrett. And I'll start with reviewing some of the features of these variants of differential algebra. I'll start with differential algebra that we are all familiar with. So I'll say differential algebra, differential algebra, differential algebra. Then we all know this has an analog that has many features in common with differential algebra, difference algebra. And there is this third type of algebra with operators that could be called arithmetic differential algebra. Differential algebra. There is actually a fourth type of algebra with operators, and there's a little theorem that says that these are the only 4 types of algebras with operators that satisfy some axioms. But I always hated this fourth type, and I couldn't find any application for it, so I'm going to disregard it and pretend it doesn't exist. So these are the 3 that really count, and actually there are some axioms. You can put one more axiom to kill this one. I'm gonna do away with it. We all know differential algebra is about fields, say, let's call them capital F with derivation. Of course, instead of fields, you can take rings, etc. Difference algebra is about rings. Maybe I should also consider fields with endomorphisms, so ring homomorphisms. And arithmetic differential algebra is about rings. I'm going to call them O, with an operator that satisfies the following axioms. For those of you who saw this before, I apologize. But I have to write them down. So the axioms are such things which I want to call p derivations. Are not additive. They satisfy a sort of additivity up to order 0. What this CP is a polynomial with integer coefficients. That's this standard co-cycle in the theory of formal groups or in many other theories. So this thing is not additive, and it doesn't satisfy the Leibniz rule, but something close to it. So something like this: a to the p db plus b to the p dA, and the quadratic term p delta a delta b. This formula look very much like something that appears in the theory of Witt vectors, and indeed one can re-express them in terms of Witt vector theory. You also have to ask this, which is almost always satisfied, that the p derivative of 1 is 0. And actually, one can demystify these axioms by noting that if you have a delta like this, then this map from O to O defined like this, a to the p plus p delta a, this is a ring homomorphism. And vice versa, if you have a ring homomorphism that is congruent to, whose reduction mod p is the Frobenius, because you see this is the situation here. This is congruent to a to the p mod p. So if you have, as they say, a lift of Frobenius, you cannot define naturally a delta like this always, but if O is torsion free, for instance, as a group, you can, and so for all practical purposes, but not for all technical purposes, such a p derivation is equivalent to a lift of Frobenius. So almost, as I said, there's a problem with the torsion. But the theory is, yeah.
Are there any restrictions on p?
Yeah. P is a prime, first of all, a prime integer, and it's always at least 3. So the theory for p equals 2 is has some features that you don't want to be there. So p is at least 3, and you fix it once and for all. Later, I'm going to consider more primes and their interaction, and that's going to be interesting. Maybe in the afternoon I'll say something about that. But for now, I'm going to fix a p. And once again, at this stage, it looks like to have p derivation is the same thing as to have lifts of Frobenius, but actually the situation is more complicated because here you won't see this too much today, but in other contexts you see it. In this theory, you have to allow analytic functions rather than polynomials, and if you have a series in A's and delta A's and say delta squared A's, etc., and you want to rewrite it, a p-adic series, and you want to rewrite it in terms of phi, it becomes divergent. So most of the examples that are interesting are like that, actually. So in some sense, one way to think about this setting, if you allow analytic functions here, in differential algebra, usually you allow only polynomials, and here only polynomials in the coordinates and the derivatives. But here you need to allow, in order to make things interesting, p-adic power series, restricted p-adic power series in the variables and their derivatives. So if you keep that in mind, then this story looks more or less as follows. So you start with ring homomorphisms that lift Frobenius, and then you adjoin a lot of divergent series. So this is sort of this setting plus a bunch of divergent series on top of the polynomials that you have here.
What happens if you're doing this for crystalline cohomology?
There is a
You have
tight
to kill
connection.
torsion, of course. I guess from what
Yeah.
you're saying.
So as a general remark, so this story is very much intertwined with crystalline cohomology. So many of the theorems are proved using crystalline cohomology. But so that's one general remark. So there's a link, of course, because you have lifts of Frobenius, so you better use whatever is available there, and that's crystalline cohomology. So that's one possible answer to your question. But going back to the general features that I was telling you about, so this theory shares a lot of has a lot of similarities with differential algebra, and maybe less with difference algebra. And should be this column should have been in between here, because it's like a passage from this to that, or vice versa, or rather there are arrows from this to that in characteristic P and this in characteristic 0. So this is the sort of general picture. Okay, so that's the general setting. And one thing that one should mention is that maybe I should draw one more line here. So these theories interact very well with the geometry of some algebraic varieties, and these theories can be used to prove the affine results about such varieties. And the varieties that I'm talking about are abelian varieties, and Shimura varieties. Shimura varieties. Like for instance, Shimura varieties. For instance, elliptic curves and modular curves. And so there are interactions, and there are results, nice results. I'm going to just put V, I mean, I'm going to check here just to show that there are results that talk about the interactions between these types of algebras with operators and the Diophantine geometry of these things. So maybe I should say Diophantine geometry of abelian varieties and Shimura varieties. So examples of an interaction between this and that are like, for instance, the proof of the Lang-Mordell conjecture over function fields in characteristic 0 or P. Here, there's work. So there's work by Khrushchevsky and Scanlon that uses difference algebra to look at the affine geometry of those. And here there are results about Heegner points on elliptic curves that are proved using this kind of arithmetic differential algebra. Okay, so so these are. Oh, I cannot see myself. Okay. These are complicated varieties. I'm a great fan of them, abelian varieties, Shimura varieties, but you cannot explain them to an undergraduate. However, you can ask yourself, how about simpler varieties like GLN? So let me draw again this 3-column thingy and try to talk about GLN. So in differential algebra, looking at differential equations related to GLN, essentially, I mean, the first step would be to look at linear differential equations. So, a linear differential equation would look like this. So, this is terrible because this is so little compared to that. So, what I want to do is erase. Erase. That's a great concept. Erase. Erase the thing. So what are linear equations in this setting? We all know about linear differential equations. So one way to write them is you take a matrix with, say, invertible with entries in a differential field that contains f. Let's say that f could be a field of meromorphic functions on a domain, G, a field of meromorphic functions on a smaller domain, or you fix them. And A is, of course, something in the Lie algebra, say, with entries in F. And there's a whole theory, the Picard-Vecchio theory of this situation. I'm going to go back just a few moments to review this when we go to the next theories. And there is an analog of different. Again, I don't exist. I exist again. So there is an analog of this in difference algebra. You do exactly the same. But the funny thing is that for a long time I had no idea what the linear equations should be in this case. That's a funny thing. So there are analogs of complicated things that are related to Buium varieties, Shimura varieties, but when you come to the simple things, there's no analog. So what's going on? So actually, something interesting is going on. That's the theme of my talk today. So I'm going to try to organize the talk like a little mystery, because I'm not going to tell you what those things are until we get there. But let's try to see how we can set up a sort of theory in this situation. So one idea on this side is to realize that actually the so-called Cauchy logarithmic derivative, so L delta from GLN of, I could put here any differential field into GLN F, viewed as the Lie algebra, G as the Lie algebra of capital GLN, that is, this thing, delta U times U inverse, to realize that this is a cocycle. So it's a cocycle for the adjoint action, of capital GLN on its Lie algebra. And you have something similar here. It's a very non-abelian cocycle, but it's also, you get a cocycle. This is also a differential polynomial map, in the sense that it's given by polynomials in the coordinates of the matrix, and their derivatives, incidentally, derivatives of order 1, and the determinant, 1 over the determinant. So this is, you can call it a delta cocycle, in the sense that it's a cocycle given by differential polynomial maps from GLN into its Lie algebra. And you can ask whether there are such things here. So, of course, you have to have an analog of differential polynomial maps. As I said, this is a bad analog. You have to allow series. So let me just give a definition. Maybe I should erase everything. Give a quick definition. Oops. It's a tricky thing. So we won't use definition too much today, but yeah, so let's just take a working definition here. So I really need a big ring that plays the role of the universal field in differential algebra, just to simplify things. So I'm going to consider such a ring. Maybe I should put another definition first. I want to take this ring. You take ZP, you take the maximal ramified extension of it and complete it. So this looks like a complicated thing, but it's the unique discrete valuation ring with maximal generated by P and residue field, say, the algebraic closure of Fp. And this has, turns out to have a unique P derivation on it. So there is a unique P derivation on it, because there's a unique lift of Frobenius on it. And this is gonna be a sufficiently big ring where our operators act. And the definition would be that a map from R to the n, say, into R to the m, this is the same R, is a delta map if there is a restricted power series. So a restricted power series means just, oops, let's call it R of x1, xn. Maybe I should just take R here. Periodically completed, so that half means periodic completion. So in other words, you know, an element here is just a power series in x1, xn, whose coefficients go to 0 periodically. So there is an f such that, actually, I'm sorry, more variables, as you expect. And let's call these variables like that. XR, oops, periodically completed. Maybe I should call this X, this tuple X prime. As usual, you know, like in differential algebra, you assume there is a capital F like this, such that F is given by evaluating such a series at the tuple and its derivatives. These are the iterates of delta. Okay, so that's a definition, and then you can, using this, you can define a delta map between the points of any two schemes.
So this is completed periodically?
Yeah, periodically, yeah. Right. So you can define, I want to just say can define in the obvious sense, delta maps between any two sets of points, R points of R schemes. X, Y being R schemes of finite type, say. Because you did it for the affine space, then you can do it for affine schemes, and then you group in the obvious sense. So you see, these are analytic functions. What I was saying before is that if you try to rewrite these expressions, delta A, etc., in terms of phi, the new series in A, phi of A, etc., are divergent, usually. And in all examples, that's the case, actually. Not in all examples, but in a lot of examples, especially related to abelian varieties and Shimura varieties. Okay. So far, so good. So you have this concept, and then you can ask to see if there are any cocycles. So let this be a cocycle for the adjoint action, which is also a delta map. Delta map in the sense above. And you want to know if there are any. Actually, there aren't, except ones that are very degenerate. Then look what happens. So there exists a diagram like this. So GLN R is here. So this is bad news, isn't it? I'm explaining you that we're failing miserably, yeah? So, but this is a theorem. It's computation, actually. And I'm, indebted to Andrei Mischenko, I think, yeah, for a very good clue for the proof of this, actually. Which is for the case where there are no derivatives. Okay, so what happens is that you can have the determinant here, that you have the determinant. This is just GL1, of course, of R. And the claim is that you have a delta homomorphism here, which means a delta map, which is a homomorphism, into R. And you have the multiplication by the identity map. So you have a splitting like this. Everything splits to the determinant. And you can ask, hey, are there delta homomorphisms from R star to R that are interesting? Yes, there are. They are the analog of your homomorphisms. Yeah. And one example, so they're all of this form. A goes to sum of lambda I, phi to the I, C of A. The sum is for a bunch of i's. The lambda i's are in R. So any delta homomorphism looks like this. And phi is phi, is the lift of Frobenius, but who is psi? Psi is an analog of the logarithmic derivative in this theory, in one dimension, so for GL1. It looks like this. It's sum of -1. You recognize a logarithm, but also some derivatives, so it deserves the name of a logarithmic derivative, actually. -1 to the n plus 1, p to the n minus 1 over n times delta a over a to the p to the n. So it starts with the first term would be delta a over a to the p, but then it has more terms, higher and higher. Powers of delta over a to the p, but modulo p, it really looks like a logarithmic derivative, but it's a lift to characteristic 0 of that. Okay, so there's a theorem that the only delta homomorphisms from here to here look like that. That's very easy to prove. And yeah, so there are no cocycles. There are no cocycles, so what do we do? So, of course, one thing to do is do nothing, so that's it, or you look for more stuff. And actually, Yeah, I looked for more stuff. Here is this. By the way, you can ask if the Cauchy's logarithmic derivative for GLN, for instance, is the only delta cocycle.
Yeah.
And I can prove a theorem. I can almost prove that. I can prove, this is an exercise, just fun. It's the only delta cocycle that is compatible with subgroups defined over the constants. You know, because that's the case. Yeah, for somebody who wants to have fun, that's an exercise.
So why does that diagram suggest that there are no cocycles?
So any cocycle is of this particular degenerate shape, so it's not sufficiently interesting. There are cocycles, but they're very degenerate. They split through the one-dimensional case. So if you want to have a theory for bigger n, then you are kind of in trouble. Yeah.
So that suggests that it's an SLN cocycle.
It's much worse than that. It's so it's not an SLN cocycle because it factors through diagonal matrices. So its image is going to be diagonal matrices. Yeah. It's this one. Yeah. It's a terrible thing.
Yes.
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 Yeah. So it's really total failure. Okay. So what do we do? First, what we do is we change the definition of the Lie algebra. The first thing to do, let's say that G is, I want to call GLN. G, oh no, maybe no, I shouldn't. Let's take subgroup scheme of GLN. Think like SLN, SON, SPN, the symplectic group, they will appear heavily in what follows. So subgroup, a closed subgroup scheme, defined by equations like, say, Fi equals 0 in the obvious sense. Remember, the Lie algebra is defined as follows. So I'm going to call it, this is a classical Lie algebra. What you do, this is of course not completely correct, but you know how to fix it. At the level of points at least, this functor is equal to this functor at the level of points. So you take these equations, Fi, you evaluate Fi at 1 plus epsilon times something. You divide by epsilon, whatever that means. You know epsilon squared is 0, so you can do that. And you write equals 0. So epsilon squared is 0. That's the Lie algebra that we all know. That's wrong for our purposes. There are no cocycles. So what we do is we define another thing. And the way we define it is we replace epsilon by p. P is small in this theory, of course, because p is, it's small. It's not infinitesimal, but it's very small. So you can do the same thing. You really have to twist these, the coefficients of Fi by the lift of Frobenius. That's a sort of mild thing. And then you do this. So let's see some examples. So for instance, what is the Lie algebra of SL2? Well, it's, I should say you take all the A's with this property. So here you take all the A's in 2 by 2 matrices. So in GL2 of R, here you have the determinant, yeah? So the determinant of 1 plus P times something. When you divide it by P, you get the trace of A. plus p times the determinant of a equals 0. So you see, it's not the trace of a equals 0. It's trace of a plus p, the determinant. It's a little...
Yeah.
So this is not an infinitesimal, but a small perturbation. It's a little curved. It's not quite... Okay, so that sounds good to me. You can play around with SP, SO, you know, like you did show the undergraduates, things like that. But this is not a subgroup of GL2 with the usual plus, of course. But let's change the group 2. Yeah. So I want to change the group. So GLN, I'm going to give it another group structure, which is a perturbation of the group structure. And it's what you expect from that. Namely, if you want to add, you see I put a delta here. If you want to add two things, you just add them, and you add p times ab. What else? To match that thing. And then this becomes a subgroup of GL. And this is very non-commutative, by the way, so of course. You see, it's a sort of... So modulo p is the additive group, and tensor with q is the formal group. So it's a mixed thing. So it has two specialization maps, one to the additive group mod p, the other one, if you tensor with q, this becomes isomorphic to the formal group of GLN. But tensoring with q destroys the whole theory here. That's important to understand. So this theory is such that if you tensor with q, you better leave the room and change your... do something else. Yeah. So there's no... So the whole thing happens on the infinitesimal neighborhoods of the reduction mod p. It's a formal scheme, periodic formal scheme theory. Okay. Cool, so we have these things. And then this becomes a subgroup here. You can try to find cocycles. Again, there's a theorem, there's none. Unless of a very special or very degenerate way. So we did something drastic and we still didn't solve the problem. But actually there are cocycles, there are maps that are cocycles up to certain quantities of order 0 that are very natural, and that I want to explain, and we will work with them. So let me explain that. So the remark will be that there will exist. How do you write this in mathematics? There will exist. There will exist delta cocycles up to order 0. Delta cocycles up to some order 0 in a certain very rigid way things, and we will work with them.
Order 0 means?
Order 0 means not involving delta. Yeah. So, but this has no mathematical meaning, what I just wrote. It's just poetry, so let's try to find a meaning for this. Well, here's how you do it. So first, you consider an absolutely arbitrary lift of Frobenius on GLN. So let phi, I'm going to call GLN for a while. And I'm going to take phi g from the periodic completion. Okay. So, how am I going to say this? Yeah, I'm going to denote like this periodic completion. Okay, nobody does. But I will have, if I have time in the afternoon, I'm gonna consider p-adic completions for different p's. And I want to compare them, which cannot be done, because you cannot compare a p-adic with a q-adic completion. But I will do it anyway. You will see, yeah. Okay, so that's an outrageous thing that's gonna happen. But let's just keep this notation for a while. So let's take an arbitrary thing and fix it. Of course, the theory will depend on this. That's bad because this is a very general thing. You will see in a moment. It depends on a lot of parameters, infinitely many. But then I will try to pin it down. And the fact that it can be pinned down by some conditions, that will be actually the main result of the talk. So, but so far we will just take an arbitrary list of Frobenius. What is this? At the level of rings, this corresponds to R of X is a matrix of indeterminates, depth of X to the -1, p-adically completed. You know what? This is frivolous. Forget about the P. Okay, I'm not going to carry the P. If I get to talk about several P's, I will reinsert them. Okay, so you have an endomorphism of this ring that lifts the endomorphism on R. If you apply it to an X, this is a matrix of indeterminates, you get another matrix of indeterminates. I'm going to call it phi, or phi of X if you want, but this is a matrix of indeterminates. And it's going to look like this, X to the P. Look at this notation. This means that I raise every entrance to the entry to the power P. This is not a pth power of the matrix. This is just a matrix obtained, by raising every entry to the power P, plus P times another matrix. I'm going to call it delta X. So there are as many such guys as matrices with entries in this ring. So there's a whole bunch of them. Yeah. So this is. Do we know an example? Sure. An example would be you just take delta to be 0. Yeah. So an example would be phi g of 0. You apply it to X, you get X to the P like this. The corresponding delta would have the property, I'm going to call it delta 0, that if you apply it to X, you get 0. So for this lift of Frobenius, the derivation annihilates the variables. That's exactly what you see in the Cauchy theory. So if you lift the derivation, you lift it in such a way that it kills the indeterminates. So this better be an interesting one, but there are others actually. I'm gonna go back to this in a second. So there will be a twist on the Cauchy theory that is sort of unexpected. You will see in a second. Okay.
Can you say again what the capital delta is?
So capital delta is a matrix of elements in here.
Okay.
Yeah, because this is a matrix, this is a matrix, this is a matrix.
Okay.
Yeah, this is has entries in here.
Okay, just unspecified rather than by the fact.
Otherwise, So I just took it arbitrary. Okay. Yeah, it's gonna. I'll have to work a little on it because if I leave it arbitrary, you might be really mad at me. So, okay, cool. Okay, so far so good. You can call this phi of X, isn't it? But don't be fooled by this notation. This means that phi of X is a matrix whose entries are in this ring, so they are of X. And you can, of course, replace X by anything you want, and you get the matrix with coefficients in whatever the coefficients of the thing that you replaced x with are in. Most complicated English sentence I've ever created. Okay, so you know what I mean. Good, so far so good. Now I'm going to define a map that I'm going to call the arithmetic logarithmic derivative with respect to this thing. So L delta of something. Wait a minute. Where does this go? So it goes from G of R, GLN of R, say, into maybe I should say GLN of R into GLN of R. Oh, sorry, guys, sorry. I apologize. So I'm talking about G. G is GLN if you want, or any other G like this, the subgroup scheme defined by Fi. Maybe I should make a different definition where G is arbitrary, GLN. So this goes into this new Lie algebra. And it's defined like this. So L delta of a matrix is, look, so there's a formula. You might say, what's going on? If you need to look at your formula, then it's not natural enough, isn't it? Actually, there is a way, sort of fancy way to present these things that are completely factorial and schematic and everything. But in the case of GLN, that's what you get. Okay, let me show you something that's less complicated. This I should have been able to remember. That's the formula, but it doesn't involve the deltas. So let me explain the formula, because it's not entirely clear. You have two phi's here. This phi is this phi. So what you do when you say capital phi of A, this means that you replace x by A and you get a matrix. But this is another phi. This, you just take the matrix A and you apply the phi on R, the lift of Frobenius, on the entries. Yeah. So these two are different. Something like this happens in Polchin theory too. So this plays the role, it's like taking the derivative of the entries, whereas this is an algebraic expression, doesn't have any derivatives. It's a purely algebraic expression in the entries. It's a complicated thing given by some formula. But if you want to re-express these in terms of the p derivative, it's delta A minus delta of A. So you see, if delta is 0, this disappears, times what you expect, A to the p plus p times delta A, the minus 1. Okay.
Is there any analog of the differential algebra condition that the group needs to be defined over constants?
No, but I will come back to this.
Oh, okay.
This is crucial.
Oh, okay.
Yeah. Because of course, you have to ask that question, you know. If you didn't ask the question, you're in trouble because you missed something. So that's the first question you have to remember to ask yourself, but let's not ask ourselves yet.
Okay.
Yeah, I will come back to it in a second. Good. So once again, if these don't look too natural, I only one. These don't look too natural to you. It's because I just told you what happens at the level of GLN, but there's a big sort of abstract definition, not big, but abstract, that gives you the story for all any smooth group scheme. And this is correct in the sense that for GLN that's the thing, and if you take a smaller group, this is still in the Lie algebra as long as, this is the question that you asked, So you have to ask something about this group, namely that its ideal is invariant under this phi g. So that's all. So phi g or delta g is the same thing. The p derivative should send the ideal of g inside the ideal of g. Okay. Let me give you examples to show you that actually this is a tragic requirement. So we have to fix that. And fixing it is the best part of the story. Okay. No, not to fix this. This will stay. But fix the tragedy that comes with that.
Oh.
Okay, so let's see.
When you're working with an arbitrary group, not just GLN, would you take this phi of g to just be a lift of the Frobenius to just to that group?
Yes, exactly.
Okay.
Yeah, exactly.
Okay, so this discussion is about if you have a lift on the Frobenius on all of GN.
Yeah.
Okay.
That's correct. Yeah. So one can come up with a theory along the lines you suggested. Yeah. But it's easier for me to explain things like this because there are explicit formulas, so you see them with your own eyes. Okay. So let's see. Let's take this simplest lift of Frobenius, which kills the derivatives, kills the variables, and see what g's we could think of, and actually not many. So, of course, all the parabolics are like this. So, an example, let's take phi GLN. You see this here I call GLN. Let's take phi GLN to send x into x to the p. So it sends, if you want delta, I'm going to put these as indices to show that this comes with that. So this equals 0. So let's see this p. Let's take that example and run this definition with that example. Delta is 0. Delta is 0, you see. What is left is delta a times a to the p to the minus 1. So that's the logarithmic derivative. A to the p to the minus 1. So the linear equations would be so a linear equation, if you want. Now I can tell you what a linear equation is in this special case. Would be this equals something fixed, isn't it? Because that's how it is in Colchin theory. And that can be rewritten as follows. Maybe I should change A into U because U is the unknown. So I'm going to say this equals something fixed times U to the P. So that's a linear equation in this case. It has a p, so it's very non-linear in some sense, but linear in another sense. Far so good. This is actually equivalent, immediately equivalent, if you add a u to the p, if you multiply by p and add a u to the p, that's equivalent to phi of u equals, say, epsilon times u to the p, where epsilon is 1 plus p alpha. So it's not like a difference equation. A difference equation would not have this. So the groups that you get are sort of, if you want to look at Galois groups, I will talk about this. They kind of go in a different direction than they're perpendicular to the groups that you expect from difference equations. Okay, so we will get to that in a second. How about subgroups? Well, parabolic groups, or more generally, not more generally, but let's give some examples of. The group of diagonal matrices, so the maximal torus, is invariant under phi because it's defined by the vanishing of these coordinates. So if you raise to the p those coordinates, you are in the same ideal. So this is okay. So and other guys like this, let's say the unipotent, or maybe the Borel. These are have ideals sent to themselves by phi g, themselves by phi g. So, but the classical groups are not. So SLN, even SLN, SON, SPN, the ideals, say I, of these guys are such that phi g, this phi GLN0 doesn't send their ideals into themselves. So this of I is not in I. So these are sort of wrong. Phyllis asked, can one think of, she asked about subgroups that are defined over the constants. These guys don't seem, they're not defined over the constants. They depend, arithmetically they are variable. These guys are sort of isotrivial. These guys descend to the constants, and these guys don't descend to the constants. But who are the constants? Of course, when you say constants, we mean, you know, the field with one element, or its algebraic closure. So these guys descend to the algebra to the field with one element. Of course, they do in all the. There are many views on many theories of the field with one element, and they're not equivalent. But these guys are toric, so they descend to the field with one element in any of the theories. So it's very consistent. What we found is very consistent with what people should expect. These are sort of defined by monomials, so they descend to the field with one element. These are not defined by monomials, they do not. But if they do not, then we cannot study them. But they are very interesting because they're the classical groups. Yeah, so we better be able to study them. But definitely not with this lift of Frobenius. So this lift of Frobenius is not well adapted to the classical groups. We will change the lift of Frobenius to study them, to study the classical groups, and we will find for each of the classical groups another lift of Frobenius that's completely special, especially adapted to each of them. This will have a special lift of Frobenius that takes care of it. This will have another one. This will have another one. And they will not, the three are completely different. I didn't tell you who these guys are. They're the split versions of the split. So one has to take the split classical groups. Okay, and then I'll tell you what happens with those lifts of Frobenius. This won't make these guys descend to the constants either. So we just change the lift of Frobenius to study them. They should be viewed as arithmetically non-isotrivial. Okay.
You're not changing the constants. Choosing a different lift.
That's a good point.
Yeah.
So, yeah, that's a good point. So the constants on R, on the ground ring, will not be changed. They will still be the roots of unity. You know, the roots of unity are viewed as the constants.